Hello, my name is Nawasir Nicole, Group 41, and I'm going to introduce you to our project, which is Reinforced Quantum Feature Learning for Indoor Air Quality Monitoring with Ensemble Knowledge Distillation. So the content of our presentation is I'm going to first introduce you to our project, then related work, problem statement, research questions and objectives, research contributions, methodology, dataset description, results, explainable AI results, model selection, and machine learning operations, product demonstration, conclusions, limitations, references, and acknowledgement. Indoor air pollution is a critical global issue that impacts health, economies, and environments. In developed countries, there is a shift towards electricity-based appliances, which has improved indoor air quality. However, in developing regions, the transition is slow and many continue to use traditional fuels, resulting in high levels of indoor air pollution. As of Uganda, according to the Uganda Bureau of Statistics 2021, the majority of households rely on biomass fuels for daily cooking and energy needs. And this has greatly contributed to elevated concentrations of particulate matter and carbon monoxide, which are directly linked to respiratory diseases. Studies that improved cooking systems can significantly reduce pollutant concentrations, but widespread adoption remains a challenge. Use of advanced computational methods such as quantum machine learning, graph attention networks, and knowledge distillation can solve this problem. So this is where we mostly base our research on. So the articles we read include Smith, Zhang, Chen, and Gestrin and Lloyd. And these were the key contributions from Smith. And then also the gaps include sensor drift, environmental noise, limited reliability over time. And then there's also from Zhang, we got our ML models like SVM and ANN, CNN, LSTM, and then the gaps were data imbalance and computational inefficiency. Then from Chen, this was a key contributions, ensemble methods. The gaps were addressing the machine learning inefficiencies and enhancing computational inefficiency. Thank you.
My name is Namtongo Jocelyn Madrid, and I'm going to take you through our problem statements. That's the domain application problem and the computational problem. So the domain application problem is basically like the problem first, like the problem we saw that there is a problem of indoor air quality monitoring. Like people don't know the amount of air they breathe in, and this is where you see people are affected by diseases, respiratory diseases such as lung cancer, asthma, pneumonia, and we saw that there is an increasing prevalence of indoor air quality pollution due to poor ventilation, emissions from household products, and external pollutants. That's why we saw that we needed an indoor air quality monitoring system. And also, yes, people can propose solutions, but then we saw that our solution of using an air quality index that is going to use a data set to contain the pollutant concentrations within a closed room is very good. That's why we had to source our data sets. That's data collection. We had to source our data set through GitHub, and our data set is called the GAMS Indoor data set. When we continue to our computational problems, these are the technical problems. Here we see computationally heavy. We shall see that some models like transformers and quantum feature learning require GPUs and the high memory to be trained, and this makes them computationally heavy. Then there is data imbalance. For example, good air quality days may dominate the data set compared to the polluted ones, causing imbalance. When we continue, there is spatial and temporary dependencies. Here, air quality varies over time and space, requiring models that account for these dependencies. So we want a model that can easily monitor the air quality in real time, like it can be able to monitor air quality in real time. Then there is hardware shortage. Some models like the quantum feature learning models require quantum simulators and quantum hardware, and that can be expensive. When I continue to take you through our research questions and objectives, our research questions include: how accurately can we predict indoor air quality pollutant levels? Our advanced models like quantum feature learning, temporal correlation networks, or transformers significantly better than the traditional methods? Which environmental features are the most critical for predicting overall indoor air quality? When we go to our research objectives, to build a machine learning model capable of accurately predicting indoor air pollutants based on historical sensor readings, to deploy a final trained model on a cloud, that's for example Render, with an API that receives sensor inputs and returns real-time air quality predictions. When we continue to our research contributions, what we were able to do. So we were able to implement an efficient feature extraction technique to handle high dimensional indoor air quality data, improving model performance. That's the heavy data. Yeah. So we also evaluated our proposed indoor air quality prediction model against existing solutions, demonstrating its accuracy and computational efficiency. Um, um, Here specifically, we are going to take you through the steps of data collection to the choosing the best model and deployment. So here we started with data collection, and that's where collect data from IoT sensors. Like it's basically finding data. Yeah. When we go to data processing, here we can carry out things like noise removal, like to specify the data we want to use. And then we go to the explanatory data analysis, whereby we visualize. That's where we shall look at the visualizations we get from our explanatory data analysis. There we shall see data cleaning, statistical analysis. That's all performed in the explanatory data analysis. When we continue to model development, we look at the models that we can use for, remember, for us, we're dealing with time series numerical data. So we look at the models that can deal with that. So we looked at the quantum feature learning model, the temporal correlation networks, the transformers, among others. Then we come to model evaluation. Here, we are evaluating our models. That's where we performed hyperparameter tuning. And on hyperparameter tuning, we performed it on our best model, and that was the temporal correlation network. Temporal correlation, that's the model we deploy. Our explanatory data analysis, this is just rather our dataset description. We are basically showing you where we sourced our datasets from. As I said, it's public and it was sourced from GitHub and indoor sensor networks. It contains data collected from various sensors monitoring air quality and environmental conditions within a specific location and environment. And so these are some of the visualizations. We got from our explanatory data analysis. And here, this is a graph that illustrates the moving average of temperature levels over a 5-day period, offering insight into consistent temperature trends over time. This is a figure that shows carbon dioxide levels fluctuating over time. And when we see this heat map, when we look at this heat map, what it shows the correlation between the features where stronger colorations are represented by the warmer color, and that is red. So we see that the colorations between the carbon dioxide humidity and PM 2.5 and 10, so we are going to see that there's a strong positive coloration, and this is seen between PM 10 and PM 2.5. And that's a red color, as we say that the stronger colorations are represented with red. And then we see that there is a moderate positive coloration between carbon dioxide and temperature, and that is represented by the orange color. And then there is we see that humidity and VOC have a strong weak negative coloration, and that's a blue color. So basically, this heat map helps identify which factors are related in the GAMS indoor data set, because that heat map is showing all the features in our data sets, and that's allowing better feature selection for machine learning models or targeted interventions for indoor air quality improvement. Thank you very much.
Hello everyone, I'm Irene and I'll be taking you through the output results and discussions. So here we had our table which had outputs for each model, and here we aimed at getting the metrics such as accuracy, precision, recall, and the F1 score. So we see that the accuracy is the general measure of how well the model predicts the overall air quality category. Precision is how good a model is to avoid false positives. Then recall is what proportion the model correctly identifies out of all the actual instances of a certain class. And F1 score is a balanced measure of a model's accuracy, more so when the classes are unbalanced. And we also have our table for the summary statistics, and it shows the distribution of the major features within the dataset, highlighting the different characteristics available for analysis. And some of the characteristics we had was the count, mean, standard deviation, the minimum, the percentiles, plus the maximum. We also had a table containing the training time and learning rate for each of our 10 models. And we see that train have the different results on carbon dioxide levels fluctuating over time, the concentration of PM10 particles over time, concentration of PM 2.5 particles, then the fluctuation of humidity levels over time, then temperature fluctuations over time. We also have that for the moving average of carbon dioxide levels plus the moving average of VOC concentrations. Then we also have the tables before hyperparameter tuning on all the models and also after tuning, and we see that we had the TCN as our best model since it achieved the best balance between fitting the training data and generalizing well to unseen data, and this is seen by the high final test accuracy and relatively low test loss. Then we also had the XAI results and discussions, and we see that the main purpose of XAI is to enhance transparency and trust by making AI decision-making processes understandable and accountable to users. So some of the benefits of XAI, we have that it enhances user confidence in AI recommendations, provides actionable and clear insights, identifies and mitigates biases in AI models, and also encourages the broader and ethical AI adoption. Then we have the LIME, and this explains model predictions by approximating them locally with simpler models. So we have our GAT LIME implementations, then the implementation of TCN with feature importance for each selected instance, and we see that here we also have that for LIME implementation of SOMs plus the LIME explanation for instance 10 with the quantum feature learning. We also have the TCN sharp implementation, and here it is a B-swarm plot, and it visualizes the contribution of each feature to the model's predictions for the GAMS indoor dataset using the sharp values.
How did we choose the model and how did we deploy the model? So our model was because this one is really designed it's used in tracking or like processing time series data. Yeah. And so this TCN helped us to track, and it had the best performance of 93%. We performed a hyperparameter tuning onto it to see whether it was the best, and a parameter tuning on it at 0.001, it was at 74.5, meaning that it was really training. It was training at an average of 74.56 and testing of 74.53. But when we went further to the number of layers, like number 3, it increased on the learning rate to 0.0005, and the training rate increased to 95.49, and the testing increased to 94.83. Deploying it, after the deployment, it was like we made it so that it could predict or monitor the carbon dioxide levels, PM10, PM VOC, temperature, humidity, to predict the air quality levels and classify them into health categories like the good, the moderate, and unhealthy. Here we start the model, then we input in the data, whereby we are loading in the data, our data set from GAMS Indo, which contains the 6 features. So it pre-processes the data, making it clean, everything. Then the data convolution network. Why did we perform the data convolution network? Specifically, performing this, sorry, why did we perform the convolution? Okay, like, why did we perform the convolution, the 1D? To check whether, like, when we are applying, so that it can capture the patterns. Is it capturing the patterns? Yeah, capturing the local patterns in your input sequence. Like in my input sequence, like let me say that if I had those local patterns, let me say the outliers, stuff like that. So it could capture them and show them to me like within this, within like the sequence. Yeah. Then why did we went further? We went further onto applying the 1D. Yes, if at all like there were no patterns, then we could skip it. Then why did we apply the causal convolutions? The causal convolutions here, these ones ensure that the prediction, like at a certain time, depends only on that data from that time t and the earlier time, so that preserves the temporal order, which is the critical time for which is critical for the time test series. Yeah. After applying that, then we combine the output to the output predictions. Output predictions, then we show the predictions, like we generate the predictions. Let me say that how was carbon dioxide? What was the trend of carbon dioxide? Yeah, within the past few days. Let me say that we're monitoring the past few days. Yeah, then we went to the, is there a loss acceptable? If the loss is acceptable, then we move. If it's acceptable, when the loss is quite low, then we move to the finalizing stage. Then what if it's not acceptable and the loss is too big? Then we go back and adjust the parameters. Yeah, I think that was it. And we'll take you through, like, I'll take you to the demonstration. What specifically was the output? That's interesting. It will prompt the user to monitor, to either monitor. If the user presses OK, then it will take the user to the to the place of monitoring, like the page for monitoring. If like there will be timestamps whereby the user will insert in the necessary